Okay, I will go ahead and start then. This is Dave Hunter, not David Banks. Hello, David. It's good to see you. And I hope that you all can see the notes that are entitled Laws of Probability, etc.
But we don't see your face.
How's that?
Ah, there you are. Hi, Dave.
Here I am. Yeah, sorry about that. There has been a little bit of internet excitement on my end. So along with all of the advantages that Eric Feigelson just outlined, comes with some downside as well. And in this case, if I disappear suddenly, I will do my best to rejoin the call ASAP as soon as I can. So good morning. At least it's morning here in the Eastern United States. And I'm going to talk to you about probability for not the next 2 hours and 20 minutes straight, but 2 hours and 20 minutes with some breaks sprinkled in there. And before we launch into this, I need to just acknowledge that the slides that you have in front of you and also available online were originally, well, these were adapted from a set of slides that originally came from a couple of folks who participated long ago in this astrostatistics workshop. And so they're acknowledged here on the title page. So I want to just begin with a prologue about like why we're studying probability to begin with. And it's a fascinating article. It comes from Nature in 1988. It's not astronomy. It's an account, almost a medical account from neuroscientists of a woman who had sustained some brain damage, essentially. And after she had surgery, she was shown pairs of pictures. These are stick figures in the pictures. They're just drawings of houses. And the two pictures that she was shown were identical, except that the house on the left side was on fire in the picture. This patient, following her surgery, turns out identified the two pictures as the same. She did not detect that one of the houses was on fire, and this is because of the injury that she had sustained. On the other hand, she seemed to be able somehow to detect that there was something amiss because, as you see on the slide, when she was asked in which house she would rather live, she reliably chose the house that was not burning. Now, reliably chose, I've put in red letters, and that's kind of where we're using that reliably chose phrase as a jumping off point today. This example was actually shown to me by a well-known statistician at Carnegie Mellon University named Rob Cass, who works in neuroscience. And I love the way that he summarizes this, right? So the thing that he loves about 14 out of 17 is that if it were 17 out of 17, we're done, right? That's pretty clear. On the other hand, if it were only 9 out of 17, well, that's just chance, right? Because she only had 2 houses to choose from when she was asked which one she'd rather live in. But now what we're given are data that say 14 out of 17 is what she chose. Now that sounds pretty convincing, but I want to do a calculation, right? And so that's kind of why we're here. And Rob goes on to talk about the fact that in many situations, there's just stuff that we don't know. For some reason, even though you do the same experiment multiple times, you're going to get different measurements. And that could be due to a variety of factors, some of which we know about, some of which we might not know about. What we're going to do, essentially, is treat the unknown part or treat the part that causes the variation as though it were generated by a gambling device, right? Because we can study gambling devices, we can understand those. That's what we're doing in a probability class. And so that's the way that we're going to treat the thing that causes our observations to differ from time to time, even though we are doing things as close to the same as possible in multiple repetitions. So that was kind of the first part, the why study probability. But just to make this a little bit more astronomical, even though it's a little bit of a toy couple of examples here. Well, first we'll start off with the old coins, the standby that's often used in a probability class. So is a coin flip random? Well, no, not really, right? If you knew enough about the situation, if you could describe how the coin is propelled into the air and you knew everything, you could pretty reliably predict what's going to happen, right? On the other hand, we don't typically know all of those things at the time a coin is flipped. And so we can treat it as though it's a gambling device. And of course, in this case, it really is a gambling device. Maybe more pertinent to this particular context is just a simple, stupid example. Right? What happens if you don't understand what causes a solar eclipse, right? You see that this happens some of the time, but you don't really understand the mechanism behind it. So maybe you model that as random. Later on, of course, you learn more, the science progresses, and you understand completely the phenomena that create eclipses, right? So you no longer have to treat the occurrence of an eclipse or any kind of an event as a random event. There may still be some randomness due to things that you don't quite observe, right? But the point is that there's always in science some things that we're trying to know about, right? And some of those things may result in measurements that vary from repetition to repetition. In probability, what we're doing is providing a mechanism to model uncertainty, as shown in red type on this slide, right? So we want to provide a mathematical structure to the notion of uncertainty. And by the way, what I like as kind of a way of understanding what random means predictably unpredictable, right? And it's that predictable aspect of the unpredictability that we can talk about in a probability context. So this is as opposed to, say, chaotic behavior, which is unpredictably unpredictable. We're not talking about that. We're talking about unpredictability that we can get a good handle on mathematically and thereby predict long-run behavior. So how do we get into the mathematical formalization? Well, before I begin, I mean, this is an incredible crowd to talk to, right? I'm looking here and it looks like there are 363 participants, which is astonishing. I've given lectures on probability to this group, this Astrostats group, many times. I'm being asked, to move their cursor from the screen. Yes. Of course. And by the way, at some point I may actually ask whether you can see my cursor. I apologize if it has been obscuring things on the screen. I hope that when I need the cursor, it will actually serve as an effective pointer. I hope that's the case. I may ask for somebody to give me some feedback on that. But why is this such an astonishing group of people to talk to? Well, because first of all, you bring an enormous degree of mathematical ability to the picture, and yet, from past experience, what I've learned is that you don't know yet very much statistics and possibly even very much probability. So as a result, we can turn a fire hose on you all. We can basically just sort of inundate you with what I like to think of as essentially like the equivalent of an undergraduate degree in statistics over the course of 1 week. And because you come to this party with so much innate mathematical talent, you actually end up getting quite a bit of it, right? So I use that. I wanted to sort of relate that to you because your intuition for probability will actually take you pretty far in this particular instance. So, right, you all know that if I show you a coin and tell you I'm going to flip it, you know what it means to say that there's a probability of a half for both heads and tails. Similarly, if I roll a die, you know what it means to say that the probability is 1/6 that I will see a 5 on that roll of the die. You can tell me if there are a million lottery tickets. You can tell me what the probability is of any one particular number winning, right? So your intuition will carry you quite far in probability. Although I will mention right at the outset that there are a couple of instances in which your intuition may fail you. There are some surprises lurking, and I will try to point those out as we go through them. Some of them are not that important for us. But they're just sort of interesting, and because again of your mathematical maturity, you may find them just of general interest. So again, with the mathematical formalization, we're going to define something called the sample space. And in a probability experiment, that's just the set of possible outcomes. And you may wonder, well, what is the definition of a probability experiment? We're not going to try to define that. It's what you think it is, right? It's something that happens that produces an outcome that we don't know a priori, right? And so if you were to list all of the possible outcomes as a set, that's called the sample space of the probability experiment. And in the three examples that I showed you on the previous slide, each one of those is a finite set. In the case of the coin toss, it's heads and tails. And here I want to make the point that the sample space is very much not a set of numbers. Right? These outcomes are totally abstract. The outcomes can be defined based on the context of the probability experiment that you're running, right? So heads is a completely legitimate outcome to put into the sample space. And of course, in a probability setting, usually every outcome is going to be assigned a probability, and that probability assignment comes from the physical understanding of the experiment. Right? And again, you all know about the three examples that I already showed you. Now, this finiteness of sample space actually means that life is good. There are no surprises lurking. In the case that the sample space is not just infinite, but uncountably infinite, then there are a couple of things that you got to be careful about in a probability setting. And I'll mention those as we go through this. Right. So discrete in the probability context means either finite or countably infinite, right? And essentially those two things are equivalent in a probability experiment, probability setting. Countably infinite is fine, right? It essentially inherits all the nice properties of finite set, more or less. Right. So let's see. Do I need to say anything more about that? Probably not. Yeah, we just use the word discrete. That's what discrete refers to, finite or countably infinite. And here we get into the technical word of warning. In the case that our sample space is uncountably infinite, then we got to be a little bit careful, right? So at the top of this slide, what you see is a definition of something called an event. Now, an event is a subset of the sample space. Could it be any subset? Yes and no. In the case of a discrete sample space, any subset is an event. On the other hand, in the case of an uncountably infinite sample space, that's where you have to be a little bit careful, because you can run into problems if you define any subset of the sample space as an event. So what we do in such cases is we talk about measurable events or measurable subsets. And in fact, if you're getting really technical about this, then a probability space is not just the sample space, but also a set of subsets of the sample space. Now, again, generally, if it's a discrete sample space, then the set of legitimate subsets is all the possible subsets. It's the power set of omega. On the other hand, if omega is uncountably infinite, then you got to be careful. Oh, goodness. And I left my cursor on the screen once again. I apologize for that. I will try not to obscure anything with my hand. Actually, and I take it from Nicolina's question in the chat that in fact, my cursor is visible. So again, I hope that when I actually need it to point to things, that will remain the case. Okay. So that's sample space. Set of possible outcomes. Now what we're going to do is link a sample space with things that we can measure, with numbers, right? So a random variable is that link. A random variable, defined rigorously, is a function. It's a function from the sample space to the reals. Full stop. Now, again, there's a bit of a technical caution here. If you're dealing with an uncountably infinite sample space, then there are certain functions from omega to r that can get you into trouble. And so in that case, we only want to allow what's known as measurable functions, right? So technically speaking, a random variable is a measurable function from omega to the reals. But usually we don't have to worry so much about these technical details as long as we're not trying to prove anything rigorously. Okay, so just from a simple die roll of a six-sided die, right? The outcomes are 1, 2, 3, 4, 5, and 6. Now remember, outcomes can be arbitrary, they can be general. So in red at the top of this little table where it says outcome, those should not necessarily be interpreted as numbers. Even though it says 1, 2, 3, 4, 5, 6, those should be interpreted as the physical manifestation of one dot occurring as we roll the six-sided die on a table, right? So that's kind of a physical reality, but we abbreviate it by 1, right? Because that's much easier than writing the long thing out. On the other hand, in the second row of this table, those really are real numbers. And what we're going to do in this particular case is we're going to assign each outcome in the sample space to its very own real number. And this is totally arbitrary. There's no rhyme or reason to why these things are doing this. But notice that there's no, you don't have to have unique values. So for instance, the value 4 is assigned to from 2 different outcomes. Let's see, and I have a question. Some participants are asking why you say. I don't know what the rest of that question is. Why do you say uncountably infinite? Ah, yes. Sorry, let me just interrupt this slide, and I apologize. So what I should have said was that if you're not familiar with sort of the alephs, aleph naught and aleph 1, the fact that there can be different levels of infinity, right? So let's just think of the number of the number of integers. Let's just start with the number of integers. Obviously, the number of integers is infinite. However, it's countably infinite. By countably, in this context, what I mean is that you can assign a one-to-one correspondence between the natural numbers and the integers, right? The natural numbers are 0, 1, 2, 3. If you can assign a one-to-one correspondence between natural numbers and your set, then your set is uncountably, sorry, it's the other way. It's countably infinite. And the word countable here refers to the fact that it's denumerable by the natural numbers. There are some sets that are provably not of that kind, right? So you can prove that the number of real numbers in the unit interval from 0 to 1 cannot possibly be associated in a one-to-one fashion with the natural numbers. That makes it an uncountably infinite set. And so that's what I meant when I talked about the 2 different kinds of infinite sets, right? One infinite set can be counted. You can number them with if you need to a string of natural numbers that never finishes, and in the other sense you cannot enumerate them. That's a fantastic suggestion from Nicolina. In fact, I should probably change my slides so that those that top line of the table is a bunch of pictures. Like there's a picture of a 1 and a 2 and a 3. That would be a much more elegant way than explaining it in words as I've done. Thank you, Nicolina, for that suggestion. So anyway, back to our slide. We can talk about various events here, various subsets of the sample space. Right? And for instance, we can refer to events by the value that the random variable assigns to them. So as you see here, for x equals 0, we could talk about the event, and this is kind of shorthand now, the event that capital X is equal to 0. What that refers to is the subset that contains only the outcome 3, for obvious reasons. Right? This is merely just a way of introducing some shorthand. We can talk about the event that x equals 4, and that would be a subset that contains outcomes 4 and 6 because of the way that our random variable assigns outcomes to real numbers. Another little bit of notation here, the capital X is usually going to be referring to a random variable, whereas the lowercase version of x usually refers to a particular value that capital could take, okay? And if that seems a little confusing, and if you're wondering why we would ever use the lowercase and the capital to mean different things, you are correct. But I should tell you that there is a huge amount of literature that already does this. And so I just wanted to alert you to the fact that in the context of a probability textbook, quite often a random variable will have a capital letter associated with it, often a capital letter towards the end of the alphabet. And a particular value that random variable can take often has a lowercase letter associated with it. Okay. So we can, if we have assigned probabilities to the outcomes in our sample space, then we can also assign probabilities to certain values that the random variable can take. And just as an example here, and this is just some notation here, if I were interested in the probability that capital X takes the value 4, and I happen to have assigned equal probabilities to each of the 6 faces of the die, then the probability that capital X is 4 is the probability that I get either outcome 4 or outcome 6, which is 1/3. Okay. Now, in any context, we always want to define our probability measure in such a way that if I have disjoint events, that the probability of their union is the sum of their probabilities. I apologize for the weird abbreviation at the top of the slide. That's how I could get it to fit on the top line, right? So for disjoint events, it's always the case that the probability of their union is the sum of their probabilities. That is one of the axioms of probability. And by the way, I just have to, I think you can you all see the chat? Can somebody tell me if all the participants can see the chat window? Can you all see that so that I don't have to like, okay, wonderful. Thank you, Allison. Yeah. And of course, I apologize for prompting that avalanche of responses. But check out Tom Laredo's quote. Tom's a fantastic astrostatistician from Cornell University, and he has a quotation there about random variables. And you know, that quotation is not wrong. All right, so back to our slide, right? So the probability of a union of disjoint events is always the sum of their probabilities. Now, and this is true not only for 2 events, but for countably many events. Now, here's where, again, sometimes technical details are important. It is not the case that if you have uncountably many disjoint events, that the probability of their union is the sum of their probabilities. And the most obvious example would be simply the unit interval. The unit interval consists of uncountably many real numbers. If we're going to assign sort of the standard probability measure to that, it would basically take any interval and assign that interval its length as its probability, okay? In that case, then every single real number has a probability exactly equal to 0, not approximately 0, not epsilon for some small epsilon that's positive. The probability is exactly 0 for any real number if you take the real interval from 0 to 1 and give it the usual probability measure. Okay, but we also know that the probability of the entire unit interval must be 1, and that is the union of uncountably many real numbers. And so again, if you have uncountably infinitely many disjoint events, it is not necessarily the case that the probability of their union is the sum of their probabilities. Right? So this is an instance where sometimes we do have to worry about some technical details. Okay, so more notation slash terminology. PMF, probability mass function, is a way of summarizing the probabilistic properties of a random variable. Basically, it's just a listing of all of the possible values that the random variable could take, together with the probabilities that it takes those values. And for our little toy example, what we saw is that capital X can take any of the values 0 to 4, -2, or 8. You see here the probabilities of those respective values, and then any other value that we might posit has a probability 0 according to our random variable. I already alluded vaguely to axioms of probability. Here are the axioms. So we have non-negativity. We want always for the probability to be at least 0. We also have this property that if you take as your event the entire sample space, which by the way is always a legitimate event. The empty set and omega itself are always going to be legitimate events, no matter how you define the set of subsets of omega that will be called events. And furthermore, the probability of omega is always 1. So that's our second axiom. And then the third one is this countable additivity, which is that the probability of a union of disjoint events is equal to the sum of the probabilities of those events. Okay, and that's true for countably infinitely many events, but not uncountably infinitely many. And so that's why countable additivity is one of the axioms, but there is no such axiom as uncountable additivity. That doesn't work. Okay, so how about non-disjoint events? I'm certain that you all have seen this, probably like second grade when they've introduced Venn diagrams to you, right? So if you want to talk about the probability of the union of A and B, well, you start by adding the probabilities of A and B, and then you subtract out the probability of the intersection. Now, of course, if A and B are disjoint, then you're subtracting the probability of an empty set, which is always 0. And by the way, the probability of the empty set being 0 follows from the 3 axioms, right? So that's why we don't need to list that among the axioms. All right, so we have to subtract the probability of the intersection generally. It turns out that this very simple sort of grade school result that I'm sure you've all seen before generalizes in a way that maybe you haven't seen. So I want to show you the generalization. Anytime you have the union of, let's say, finitely many events, then you can express them using this thing called the inclusion-exclusion rule. I should say that you can express the probability of their union using the inclusion-exclusion rule. And the way it works is illustrated here for 3 events. If you want the probability of the union of A, B, and C, you start by adding the individual probabilities, then you subtract out all of the probabilities of the 2-way intersections, but now you've gone too far in your correction, so now you got to add back in all of the probabilities of intersections of 3 events, and then you alternate back and forth this way. So you start with the probabilities, then you subtract out the 2-way interactions, you add the 3-way interactions until you finally get to the end, right? So however many events that you started with. And by the way, this is kind of a fun, if you're not familiar with this inclusion-exclusion rule, here's a little bit of a homework assignment you might try. Prove it. It's kind of a neat use of mathematical induction, and I can tell you from experience, having assigned this problem to many probability students over the years, it's non-trivial. It's not hard, but it's also non-trivial, and it's kind of interesting. Okay, so here we go. You can, if you want, set up your sample space in such a way that every outcome has the same probability. And so on this slide, which, yes, I'm not occluding in any way, on this slide, lowercase m stands for the number of outcomes in the sample space. And in this case, what I'm saying then is that every outcome has probability 1 on m, 1 over m. And that means that in this discrete sample space setting, any event has probability that's determined simply by counting the number of outcomes in that event, right? So in my slide, I have an event that's titled A. And so the probability of A is simply the cardinality of A divided by m. In other words, the number of outcomes in A divided by m. And when you have something like this set up, there are some things that suddenly become sort of strikingly non-obvious, right? So just combining this slide at the top with what you saw on the previous slide, the inclusion and exclusion rule, which seems so simple, you actually get this striking result. It's sometimes, let's see, the matching problem is what it goes by, right? So if n people shuffle their hats, what's the probability that at least one person gets their own hat back, right? But there's multiple ways of framing this. For instance, you can take 2 decks of playing cards of 52 cards each, right? And they're identical except that they're shuffled, and so they're both in random order. And then you start turning them over one at a time. And you can make a bet with your class, and I say this having done it many times, you can make a bet with your class that you're going to see a match, an exact match at some point as you flip through the 52 cards. Intuitively, human beings seem to not like this very much. They seem to think that there's a small probability that you will see an exact match, when in reality, the true answer is about 63% of a match. It is almost exactly equal to 1 minus 1 on E, 1 minus 1 over E, which is exactly 63%. And this is an astonishingly good approximation. So if you're talking about 52 cards, then basically this is accurate to within 1 over 52 factorial, which is a super small number, right? So the approximation 1 minus 1 over E is a really, really close approximation to the correct answer. And so, you know, as again, you can astonish your friends and win money because it's a fairly counterintuitive result. And again, if you want a homework question or a homework assignment, just try to prove it. Try to prove this fact using inclusion exclusion. Okay. So again, because we can set up sample spaces so that they have equally likely outcomes, we can base our probability calculations on simply counting the number of outcomes in a particular event. And I just want to throw in a word of caution here. Now, this is something that I know all of you would be familiar with already, but just to sort of remind you, right, you have to be very careful, because when you say equally likely, you have to make sure what is equally likely. In this case, what I've done is I've said that we're going to flip 3 coins and we're going to count the number of heads. And I will define a random variable equal to the number of heads in 3 tosses of a fair coin. Okay. Now, in this case, I would say that the sample space consists of the 8 possible outcomes based on what happens on your 3 tosses, right? 2 times 2 times 2 is the number of outcomes in that sample space. On the other hand, if I assign X to be the number of heads I obtain, suddenly the possible values of X are not equally likely, even though the outcomes in the sample space are equally likely. So this is just sort of a word of warning that even though you're in a sort of a quote equally likely setting, you have to be careful what is equally likely. Okay, so because I'm on the schedule for 2 hours and 20 minutes, which is crazy, I'm going to just pause here for a few minutes. If you need to get up and get a drink or something, please go right ahead. And I'm going to scan the chat here for some questions.
Yeah, Dave, there is a question in the Q&A that says, could you connect the reals and the outcome space to the table again?
The reals,
it was a few slides ago.
Is it this one? Do you happen to know? Is that Claire?
Yeah, that was me. I'm not sure if it's this slide.
Let's see, 2 people. Let's.
Yeah. Okay. Kristen says it's this slide. Yeah.
And the question was to connect the reals to the outcomes again. Was that the question in a nutshell?
To the outcome space, yeah.
Yeah. Okay. So first of all, let me. So I'm going to ask you to imagine something that instead of these red numbers, the numbers 1, 2, 3, 4, 5, 6, that we're actually following Nicolina's fantastic suggestion from the chat. Nicolina suggested that instead of those numbers, I should have just included pictures. Right? So imagine that this number 1 is not the number 1, but it's rather the die sitting on the table with 1 dot showing. Whereas this is not the number 2, it's a die with 2 spots showing. And this again is just the die having landed with 3 showing, right? So these outcomes are physical things that happened in my probability experiment where I roll a die on a table, right? Now, what I'm going to do is I'm simply going to define a real value that's attached to each of those possible outcomes. And if the question is, where did these numbers come from in black, these net dollars earned, I have no idea. This is totally arbitrary, right? Somebody has simply said that if you roll a 1, then you lose $8 or something like that, right? Whereas if you roll a 2, then you win $2. If you roll a 3, then you break even, right? Somehow we're going to determine a rule that assigns to every physical reality from our probability experiment a real number. And that assignment, that function from sample space to reals is called a random variable. I don't know if that addresses the question or not.
There is another question in the Q&A. It's about what's the difference between disjoint and independent events?
Oh,
David,
very good question.
David, you can
And
find the
so
Q&A.
what I like to tell, sorry, go ahead and Tech.
Oh, you can find the Q&A on the bottom bar.
The Q&A on the bottom. Oh yeah, sure enough. That's different from the chat, isn't it?
Yeah.
Oh yeah, I'm really glad you pointed me in that direction, Tak. Thank you. Okay, so Sayan has a terrific question that is frankly asked every single time I teach this to probability students. What the difference between mutually exclusive and disjoint, mutually exclusive, which is the same as disjoint, and independent. So first of all, I will say, hold off on independent for the time being. However, what I can tell you is this. In a Venn diagram, you cannot depict independent events, okay? A Venn diagram will tell you if two events are disjoint, mutually exclusive, but a Venn diagram cannot tell you anything about independence because independence has to do with the specific values that we assign to the two events A and B and to their intersection. Okay, so independence is a totally separate concept from mutually exclusive. And I will go farther than that to say the following. If you have two events that are mutually exclusive, that is as far removed from independence as you could possibly be. So they're sort of like completely disparate concepts. They're not even the same thing ever at all. Please repeat the few slides on probability based on counting outcomes if possible. You know what? So what I will say in regard to the please repeat the slides is that you have access to the slides. And I think it's probably best instead of going back over slides in the time that we have, for me to keep moving forward. I will certainly try to address specific questions about the slides, but I'm going to sort of refer you all to the slides if you want to go back and review specific slides again. What's the expression for the inclusion based on n events? Aha, Ines. So basically you simply start with this pattern, right? Here's the pattern. Repeat this pattern, right? So if you have n events, then the probability of the union of those events is equal to, first of all, the sum of the probabilities of the individual events minus the sum of the probabilities of all two-way intersections plus the sum of the probabilities of all the three-way intersections, minus the sum of the probabilities of all the four-way intersections, etc., until you get to the last stage, which is the intersection of all the events together. And it either has a plus or a minus in front of it, depending upon whether n is even or odd. Let's see. I'm just confused because I thought the sample space sampled the reals. No, definitely not. So, well, and I'll tell you what, and this is Kristen's question. In reality, Kristen, I'm making a bit of a mountain out of a molehill here. You can, if you want, sort of visualize the problem in a way that the sample space really is the values that the random variable takes, because we're almost always interested in what the random variable does. And so it's not super crazy to think of the sample space as the set of reals that's mapped to by that random variable. Okay, but generally speaking, like just to be technically correct here, the sample space is not a set of real numbers. It could be, depending on the context, but generally speaking, the sample space is the set of outcomes of my probability experiment. These outcomes could be completely general, abstract happenings. In the case of coins, it'd be heads or tails, and how we choose to depict that is kind of up to us, but that's certainly not real numbers, right? Oh, sorry, good question, Lauren. Axiom, A-X-I-O-M. An axiom is a mathematical fact that does not arise from any facts below it, if you will. In other words, it's an assumption that we make at the outset. And then we go on to prove a lot of things built on the scaffold of the axioms, right? So in a probability context, typically what we do is we assume just these three things, and from there we end up proving lots of other stuff. But an axiom is just accepted as true without proof. And Martin's question, let's see. Could you please repeat what a legitimate set is? So I think what you mean is a legitimate event, right? So a legitimate event is a measurable subset of the sample space. And if you've had measure theory, then just imagine that your sample space really is, in this case, a set of real numbers. Okay, and in that situation, we would only want the measurable subsets, typically speaking, to be qualified as events. Oh, and it looks like Ian is going to answer this question live. Fantastic. Okay. Is there an astronomical example of a matching problem? That is a good question, Antoine, and I don't know the answer to that question. I will leave that to my esteemed colleagues. However, what I will say is that the matching problem has various guises, and I would not be at all surprised if it comes up. So sort of hold that thought. That's a very good question, and the short answer is I don't know. Okay, so maybe I can just arrange my screen here so that the Q&A and the chat are not occluding anything. Okay, and Julie asks, a subset of the sample space can be just one number. Is that also an event? Usually a singleton is considered an event. Depends on how we're going to define the legitimate events, but in most contexts, yeah, singleton is legitimate as an event. And it may be that a singleton always has probability 0. It may be, as we have seen, that because our sample space is discrete to begin with, that every singleton has some non-zero probability. So it depends on the context whether the event that consists of a singleton has probability 0. Okay, so back to the slides. And for each of these breaks, I just threw together kind of a synopsis of like what I think are kind of the big ideas. And so just to remind you, your intuition is going to be super useful, and that's going to be the theme as we move forward here. Even though it's sometimes possible to fool it, as in the case of these sort of like uncountably infinite sample spaces sometimes. The two concepts that are underlined there, random variable, it's a function from the sample space to the reals. Event is basically a subset of the sample space, give or take some technical issues sometimes. And it turns out that if your sample space is discrete, then the mathematics is straightforward and there are no technical things you got to worry about. Okay. So here we go, conditional probability. Speaking of intuition, your intuition of conditional probability is just what you thought it was, even if you've never heard this concept before. So let me just sort of walk you through, and I apologize, these slides are very wordy, but let me just walk you through a thought experiment. So once again, we're gonna throw a die, a fair 6-sided die. We're gonna just see what we get in one roll of that die. And now I'm going to define my random variable to be the number of dots shown. So in this case, the random variable x really does have values 1, 2, 3, 4, 5, or 6. Those are now real numbers. Right? So what is the probability? What is the probability that x lies in this event? Okay. Well, immediately most of you would answer, okay. I'm seeing that I froze a bit. Can anybody tell me if I'm back?
You're back, but you.
Thank you. Okay. I apologize for that. I think probably because, well, we don't need to get into because. I'm glad I'm back. So what I was saying is I'm interested now in the probability that the outcome of my random roll of a die lies in the set 1, 2, 3. And I should say the event 1, 2, 3. And immediately all of you know that the probability is 1/2. Okay. So now I'm going to change the question slightly. I'm going to give you some extra information. And thank you to all who are telling me I'm back. I appreciate it. So here's the extra information. So I've rolled the die, and the extra information is that the answer that I got, the result, is somehow in the event 2, 4, 6. Okay? Don't ask me how I know that. Just bear with me for the moment. I'm going to give you that extra bit of information. Now, conditional on that new information, what's the probability that X lies in the event 1, 2, 3? I think that most of you would agree that that probability should be 1/3, right? Why is that? Well, it's because if I know only that I'm in 2, 4, and 6, that means that there's a 1/3 chance that it's 2, a 1/3 chance that it's 4, and a 1/3 chance that it's 6, because my original sample space had equal probabilities. Therefore, the probability that I'm in 1, 2, 3, which in this case must mean that it's equal to 2, is just 1/3, right? Because that's the new probability assigned to the outcome 2. Again, I think it's a fairly simple story to tell, but one where most people answer intuitively. So please notice that the answer changed. My original answer was 1/2, but conditional on some new information, my answer changed. Okay, that's going to be a theme for the next few slides. In conditional probability, what we're doing is introducing some new information and seeing how that changes our probability calculations. And by the way, I want to sort of give you a sense for where this is heading. The new information, scientifically speaking, are the data. So what we do is, if you're doing this in a Bayesian context, which we'll talk about in a minute, we start with an a priori sense for what may have been true. We now add the data, and we see how those data modify our a priori notions. Okay. And that's what conditional probability is all about. And we have some notation for this. Is this similar to the Monty Hall problem? Excellent question, Allison. Stay tuned for the answer to that. The answer is yes. So that's a terrific question. You read my mind. So down here in the right-hand bottom right, this notation, P of A vertical bar B, is read or spoken as the conditional probability of the event A given the event B. In other words, if I told you that B has already occurred, what is now the new probability of A? Okay. So of course, in my story here, A is the event 1, 2, 3. B is the event 2, 4, 6. Okay. All right. So here's how we define conditional probability. And this completely matches our intuition. If you were to think through the previous slide, you would come up with this formula on your own, I guarantee it. In other words, if I were to ask you, what is the formula for P of A given B? You would eventually arrive at this, right? We take the probability of the intersection and we divide it by the probability of B. And if you want to, you can just sort of think through in your brain, like, does that check out with the previous one where A was 1, 2, 3 and B was 2, 4, 6? Well, sure it does, right? Because think of the intersection. The intersection of A and B in that case would be simply the singleton 2, right? That has probability 1/6. The probability of B, the probability of 2, 4, 6 is 3/6, 1/3, sorry, 1/2, right? So now this conditional probability is 1/6 over 1/2, which is 1/3. I love that the anonymous attendee says, oof, Bayes' law. Yes, we are heading in the direction of Bayes' law. So I apologize if that makes you say oof, but that's where we're going with all of this. All right, so in the case where our sample space has uniform probabilities, that means that just as we did a few slides ago, we can just count. We can count the number of outcomes in the events to determine what these probabilities are or what these conditional probabilities are. And I won't walk you through the algebra on the bottom of this slide. It's not super exciting. Okay, now get ready for some really complicated algebra. We're going to start with this rule that I claim is completely intuitive. This is, I claim, exactly what you would have come up with. And then see if you can see how we got from that to this, right? Woohoo, some pretty strong algebra there. However, I would say that it is a deceptively simple equation that is staring at you from the middle of this slide. We're going to call this the multiplicative law of conditional probability. Another way to express it is that the probability of the intersection can be expressed as the product of the conditional probability times what's called the marginal probability, for reasons that are not important right now. So P of B times P of A given B gives you P of A and B. Okay, and that's the multiplicative law of conditional probability. Now, many times when you see multiplication of probabilities, people always go to independence. And sometimes they're wrong about that. You know, multiplication of probabilities happens all the time in real important problems. And it's sometimes because we can claim independence, but more generally, it's because of this multiplicative law. And I could cite some examples of people who should really know better, claiming that the reason that we multiply these probabilities is because the events are independent, when the events they're talking about are clearly not independent. You don't need independence to multiply probabilities as long as you are in this situation and you can claim that you're using the multiplicative law of conditional probabilities. And just to sort of give you a sense for how powerful this might be, let's just take this out a couple of steps. Let's suppose we want the probability of the intersection of more than two events, right? We have n events here, A1 through AN. Well, we can do a telescoping version of the multiplicative law. We can start with the probability of A1, then multiply by the conditional probability of A2 given A1, then the conditional probability of A3 given A2 and A1, and so on, and build that up one event at a time if we have some way of knowing those conditional probabilities. You say, well, where would that ever come up? Here's a very well-known situation in which they can come up. Let's suppose you have n people in the room and you want to know what is the probability that there's at least one pair of matching birthdays. And let me just back up for one sec. The question is, aren't the events A given B and B independent? Yes, technically speaking, but that gets a little bit tricky, right? So when you condition on something, then that thing is independent of the thing you conditioned on. And one way to think about it is this, especially when you're dealing with random variables. If you condition on a random variable, what that basically means is you're now going to treat it as though it's known. In other words, it's now fixed. It's a constant. It's no longer random. And everything is independent of any constant. Okay, so it's a very good question. So hold that thought as well. So back to the birthday problem. And this is, again, something that I've done many times with introductory probability classes, because it's really one of these situations that is not what intuitively seems obvious, right? So if I have a class of like 60 students, I can come up here and announce completely confidently that there are two of you in this room that have the same birthday, right? Because I know full well that the probability is, you know, pretty close to 99% or whatever, right? So this birthday problem is easy to solve, or it's easy to understand how to solve it using the multiplicative law of conditional probability, right? So, okay, what we're going to do is we're going to work on the probability of not seeing a match, and then we'll just subtract that from 1, right? So probability of 1 minus the probability of no match should give us the answer. So Aditya's already going to do that. I got to tell you, Aditya, there are 362 participants, so I can say with complete certainty that we're gonna have some matching birthdays here. So the reason that you have this telescoping product, at least one way to see why you have this telescoping product, is to, well, I'm going to go back a slide. Is to break it down like this. Okay. So let's define some events. Let's do it cleverly. So A1 here is the event of no match after seeing one person. Okay. A2 is the event of no match on that second person. A3 is the event of no match after seeing 3 people, and so on. So I know the probability of no match with one person, that's 1. There couldn't possibly be a match with one person, right? Now, what about the conditional probability of no match on the second person, given that there's no match with the first person, which was a certainty? Well, that's easy as well, right? 364 over 365 is obviously the probability of no match, and let's not worry about leap years. Now it's when it gets interesting, though. When you get that third person, what's the probability of A3 given A1 and A2? So here's where you actually need the conditional probability, right? Because when I ask you, what's the probability of seeing no match with that third person, you need to know that the first 2 were distinct, right? Because otherwise you can't tell me that the probability of no match on the third person is 363 over 365. Because if those first two did happen to match, then that changes the probability. So the 363 over 365, which is the third term here, is a conditional probability of no match for the third person, given that, in other words, if we already know that there was no match on the first two people. And that's why this telescoping sum works, because in each case, it's a conditional probability, given that we know that there was no match that came before it. And that's how we get the birthday problem. And of course, who's the first person that puts the number of people in the room before you get to a 50% or larger probability of a match? You got it, Joshua. Joshua wins the birthday cake shown in this slide. All right. Let's see. I think I need to say nothing more about this. Yeah, so let's move on. Okay, so oh, yeah. So, an anonymous attendee is going to call me out here, correctly so. And let me tell you that there's one embarrassing incident in my past as a math teacher. This is back when I was teaching high school math, right? And let me just preface this by saying one of the things that I tacitly assumed in that previous problem was, first of all, that all 365 days were equally likely, and secondly, that the birthdays were independent of one another. So the embarrassing story from my past was the smallish class that I had. I was teaching prob stat to a smallish group of students, and I asked them, right, so what do you think the chances is that we have a match in this classroom, right? And the students actually started to laugh at me a little bit. And I was like, I don't know what's going on here. These are high school students, so maybe they're just being high school students and laughing at me for other reasons. And so I went around the way that I usually do, and I said, right, say your birthday out loud and raise your hand if you hear your birthday. And by the time I got around to the far corner of the room, I realized that the two twins were sitting over there, which is why the students were laughing at me, right? So yeah, you got to assume that there isn't some sort of strong dependence in the birthdays in order for the calculations that I just showed you to make sense. So you shouldn't have twins in the room, because then you can be fairly certain that there will be a matching birthday, and nobody's impressed by that fact. All right, so moving on to a situation where your intuition will not steer you wrong. The law of total probability, okay? And so what you see on the slide here, and my cursor is not in the way, that's good. What you see on the slide here is a sample space that is depicted as a rectangle. That's our Venn diagram here. The Venn diagram has omega being a rectangle. And you can see that it's chopped up into, looks like 7 slices, seven pizza slices. I don't know why you would cut your pizza like that, but we have partitioned, mathematically speaking, the sample space into 7 events, B1 through B7. What's the probability of there being twins in a group of n random people? I don't know the answer to that, Spencer. All right, so we've got our 7 events that together comprise all of the sample space. And in addition to that, what you see superimposed on those 7 events is another event, A, okay? So A is kind of that squiggly shape. And there's an arrow pointing to A. It's a little bit hard to understand that that's what's being depicted here, right? So we have 7 events, B1 through B7, that together are disjoint and give us the entire sample space. So they form a partition. And in addition to that, there's a new event, A. And I want to say something about A. Okay, so here's the earth-shattering prospect that I can express the probability of A as the sum of the probabilities of A intersected with each of the events in that partition. Right? It's obvious, right? I guess it's, well, let me just say it's obvious. You can prove it from the axioms. Let's put it that way, okay? And by the way, those are disjoint events. The 7 events on the right side of this equation are disjoint because our partition consists of disjoint events. By assumption, the B's do not overlap. So these intersections cannot either overlap. Okay, so we'll call this the law of total probability, and it simply says that I can break up the probability of A into pieces according to some superimposed partition that we happen to be given. Now I'm going to combine this law that I would say is fairly intuitively obvious with the multiplicative law that we already saw. Because remember, one of the ways that we can express the probability of this intersection is as the product of a conditional with a marginal. Right? And so P of A and B1 can be expressed as the product of the conditional probability of A given B1 times the probability of B1. And you'll notice here, what I'm assuming is that I actually know the underlying probabilities of the B's, right? So the partition comes along with the probabilities of those things. So if I know the probabilities of each of the B's, and I happen to know how A is influenced by each of the B's, then I can combine all that information to give me the overall probability of the event A. And here we're actually getting into the realm of the not quite so obvious any longer. And just as a way of illustrating that fact, I'll throw this problem at you. And I claim that this problem is not easy to answer without actually resorting to the law of total probability. Maybe some of you see it intuitively, obviously. But the idea here is you've got 6 coins in a bag, and one of them is a trick coin. It's got a double-headed, it is double-headed, right? So 5 of the coins are regular coins with 1 head, 1 tail. The 6th coin is a trick coin that is heads, heads. And so what you do, you reach into the bag, you shake it up at random, you grab one, and then you flip it, and you flip it 4 times, right? So the same coin that comes out of the bag is flipped 4 times, and now you get 4 heads. And there are a couple of questions that arise here, right? First of all, what is the probability of that happening, right? What is the probability that I could reach into the bag, pull a coin out at random, flip it 4 times, and get 4 heads in a row? Well, we'll call that A. And now A is actually the A from the previous slide. Okay, so now A is the event that all 4 tosses yield heads. That's going to be some subset of the sample space, right? Well, what is the probability of A? What I'm going to do is I'm going to depict it as A given that I picked a fair coin, and A given that I picked an unfair coin, right? Because each of those probabilities is easy. I claim that if I picked a fair coin, the probability of getting 4 heads in succession is just 1/2 raised to the 4th power. On the other hand, if I picked the unfair coin, then I claim the probability of getting 4 heads in succession is 1. It has to happen. And so now the only thing additional that I need is to know what is the probability of getting the fair coin to begin with, what is the probability of getting an unfair coin to begin with. Well, that's going to be 5/6 and 1/6. So I can combine all of this and find the probability of A. But now we can go one step further to the second bullet point on this slide, and that's probably the most interesting question from a scientific perspective. Let's suppose that I did this. I ran this experiment. I got the 4 heads. What I'd really like to know is whether I got the trick coin based only on this information. What's that probability? Because a priori, that probability was 1/6. But now that I've seen 4 heads in a row, it stands to reason that that probability should be larger. Well, how large? It's certainly not 100%, right? There's still some non-negligible probability that I picked a fair coin and just happened to get 4 heads in a row, right? But what is that probability? That's an interesting question. And I claim that these 2 questions are not easy to answer without actually doing some calculations. And the calculations is where the law of total probability comes in. It's where the multiplicative law of conditional probability comes in. And again, remember, those 2 facts were built completely based on our intuition, right? There is no difficult mathematics that underlies any of this. But when you combine these things carefully, what you get is some useful stuff. And so just to address that first question, here's the calculation. The probability of A comes out to be 7/32. If that was obvious to you intuitively, then congratulations. It's certainly not obvious to me. Maybe there's a way of seeing that, but I kind of have to go through the calculations. I just don't know of a simple way to see that without doing the math. And yeah, we're using independence here in a way, but we'll come back to that. You can use just the counting method to claim that 1/2 to the 4th is the right answer. So that one, it may seem like we're jumping ahead a bit, but we're not. Let's see. At some point, we're going to talk about, yes, okay, here we go. What is the probability that the coin picked was the trick coin? Okay, I should probably go back just to figure out some notation here. So again, our partition, we don't need B1 through B7. I'm simply going to use B and B complement. In fact, I think I saw that somebody had asked about a C, where you see a superscripted C that stands for complement. So it's basically everything that's not in B, right? So B will be the event that I picked a regular coin. B complement will be the event that I didn't, okay? Those two events, B and B complement, necessarily form a partition. In other words, together, their union is all of the sample space and they don't overlap. That's always the way that complements work. Okay, so now what I'm asking when I say what's the probability that it was a trick coin is what's the probability of B complement? But I'm given that something happened, right? I'm given that A occurred. Well, by definition, this is simply the probability of the intersection divided by the probability of A. But we just found the probability of A. That was the hard part. The probability of A is 7/32. What about the numerator? What's the probability of B complement and A? Well, again, we can rely on the multiplicative law of conditional probability. Again, nothing earth-shaking here, but we can express the probability of this intersection in the numerator as the product of these two probabilities, each of which I claim we know. And so in the end, what we get is 16/21. Totally non-obvious as far as I'm concerned, right? So 16/21, that's the answer to the question. What is the probability that the coin picked was the trick coin? Again, the bag has 6 coins. One of them is a trick coin. We pick one at random, we flip it 4 times, and we observe 4 heads in a row. Given that, there's a 16/21 probability that the coin we picked was the trick coin. And again, it stands to reason that that should be larger than 1/6 and smaller than 100%, right? And by the way, just to sort of frame this in larger terms, like the big picture, okay, a priori, we had a 1/6 probability of picking that unfair coin. So we have a prior notion. We now observe some data, right? The data come into this in terms of what did we see in our coin flips? Okay. And what we're doing in this calculation on this slide is we're combining our prior knowledge with the data. And what we get at the end is the probability now that given our data, we had to pick the trick coin to begin with. The good question, Aaron. 16/21 is the probability of the coin being the trick coin given A, okay? So it's just what you see on the slide. It's P of B complement given A. That's 16/21. The 7/32 is P of A. That's the denominator. That's the probability that if you set up this experiment the way I described, that you will reach in, when you reach in and pull out your coin and flip it 4 times, you will see 4 heads. That's 7/32. Okay, so here we go, Bayes' theorem. We just saw it. We just saw an example of Bayes' theorem. It's a way of updating prior probabilities using data. And there are a couple of things that I want to call your attention here too. We already talked about the partition given by the B's, okay? So here's what we would like to obtain. Okay, we want something of the form probability of B sub I, right? For given I, we want the probability of that B sub I given A. In other words, we want to know what is the probability of the individual partition things, events, given the data. What we know are probabilities that actually look like conditionals the other way around. Okay. What we know, in other words, are probabilities of obtaining 4 heads in a row, given I happen to choose the wrong coin or one of the fair coins. Okay. So P of A given BI, this is the data. This is the model for our data. We believe that we know how the B's influence the A. And Bayes' theorem allows us to reverse that conditional, because what we want scientifically is a probability of B given A, not A given B. A given B, that's the model for the physical experiment that we're running, the data collecting mechanism. In order to make this work, on the other hand, we need an additional ingredient. We need the P of BI. Now, in the coin flip experiment, it's clear what that P of BI should be. Scientifically, here's where you get into all sorts of philosophical debates. Should we be allowed to posit an a priori notion of reality before we observe data? Philosophically, right? That almost seems like it's unscientific on a certain level. On the other hand, if you don't do it, then you can't do Bayesian computations. You need to have your prior, you need to have your P of BI in order to make Bayesian calculations work. And there's just a whole bunch of literature about the philosophical debate. And it turns out that for most modern statisticians, it's not really an important debate. It used to be that it was a very important debate. People felt like they had to nail down the philosophy of Bayesian versus non-Bayesian. Most statisticians today will just be conversant in Bayesian methods and non-Bayesian methods. They're interested in doing what works, and they don't really care so much about the philosophical underpinnings. And let's see, so Anjali asks, how does bias come into play in Bayes' theorem? So bias would be, that would come about via the model. Our model for A given BI could be biased, all right? And so somehow that would have to be taken account of through the model, and generally not the prior. I can't think of a way that bias enters a prior. Yeah. All right. So, let's see. Did I talk through all of that? Boy, like I said, we could really spend days talking through the philosophical implications here. Oh, I know what I wanted to say. You know, so even if you're a little bit uncomfortable about the philosophy of the Bayes thing, right? Because you do feel like we shouldn't be sort of polluting our analysis by what we believe a priori. Well, let me offer a couple of counterpoints. Number one, there are actually legitimate situations in which we do bring some knowledge to the table. We do have a sense for how the universe operates. And if we don't throw that into our prior, in a certain sense, we're wasting that information, okay? So again, there are just some cases where we really do have a priori information. Number two, I will say this, that even if you disagree with the Bayesian paradigm, you can still use it to generate estimates that can be treated as though they were obtained by non-Bayesian methods. And the statistical properties of those estimators are optimal in the non-Bayesian sense. And so here you can kind of say, like, you can justify Bayesian methods to a non-Bayesian method simply on the basis that they work. They work as well as anything a non-Bayesian could propose, right? Using the standards of a non-Bayesian, no less. So anyway, I've already talked more than I probably should have about this. And by the way, I'm so happy to see that Tom Laredo is typing an answer. Like, Tom is an example of, you know, I hope Tom doesn't take offense to this. I consider Tom a Bayesian. I also consider him one of the world's leading astrostatisticians, right? So if you wanna have a really deep discussion about why it's okay to be Bayesian, particularly in the context of astrostatistics, I think there's no better person to speak with than Tom Laredo. So keep typing your answer, Tom. All right, here we go. Here's a picture of Thomas Bayes, or not. It's funny because if you ever see a picture of Thomas Bayes, this is the picture. It's the only picture that is even suggesting that it is a picture of Thomas Bayes. Somewhat amusingly, though, nobody really knows whether it's Thomas Bayes. And I once saw, and this sounds like a joke, but it's not. I once saw a Bayesian analysis of whether this picture is of Thomas Bayes. So I think the answer that they came up with is probably not. But at any rate, the name is Thomas Bayes. His name already has an S. So when I refer to Bayes' theorem, I will put an apostrophe after the S. And this is me being a grammar nerd. Just wanted to alert you to the fact that it is not B-A-Y-E apostrophe S theorem. That's the sort of thing that makes, you know, that just makes my hair stand on end, what little's left of it. Let's see. Yeah. Yeah, okay. So here we get down to a simple way of remembering what Bayes' theorem actually says. So let me just first walk you through the thing at the top. It looks really complicated, but remember, everything you see in the top line of formulas was built from simple stuff, very intuitive ideas. It's exactly what we think conditional probability ought to be. We're also relying on this law of total probability, which means that you can slice A into its various parts. And I see there's a discussion developing about whether B1 is the best slice and the pepperoni. Yeah, you got it, right? It's like, this is completely intuitive stuff and sort of funny if you're thinking in terms of a pizza. So there's nothing really difficult happening on that top line. Okay, but what is it? On the left, we've got the thing that we want. We want to know how the reality is changing based on the data that we see, right? So B is kind of, that's the underlying reality. We would like to know which of the B's is the truth, right? We're trying to discover the reality of things. And we observe A, we observe some data. Okay, and on the far right, what we have is, first of all, in the numerator, we have probability of A given BI. That is the model. That is how A comes about as a data as generated random data, given that we know what the reality is. Okay, so this first thing on the top is the model for the data. The second thing on the top is the prior for B. And then the bottom is nothing but a normalizing constant. And actually, it doesn't depend on B at all, right? Because even though it looks like there are B's in this denominator, you'll notice that they're summed out. So that denominator doesn't depend on B sub I or any of the B's. And so really, it's just a constant of proportionality. And in some situations, in fact, you might even argue most situations, you can ignore this denominator and simply summarize Bayes' theorem as follows, that the probability on the left-hand side, which is what we want, that's called the posterior probability, is given by the product of the likelihood with the prior, and the likelihood is the model for the data. So again, the posterior is the model times the prior, the likelihood times the prior, up to a constant of proportionality. And now back to whoever asked about Monty Hall, you know, this conditional probability often results in these, I guess you could call them paradoxes, but it's really just sort of, again, ways of revealing that human beings are not very good at thinking probabilistically. And if you're not familiar with the Monty Hall problem, I suggest that you Google it. There was for a while, and I remember this is like back in the 80s or 90s, there was some controversy over the Monty Hall problem because, you know, there was at least one or two sort of publicly visible people who posited the correct answer for this problem. And it was just so counterintuitive to so many people that they basically just sort of attacked this notion, and like they were wrong, and yet they should have known better. Anyway, it's just one of these things that human beings may not be very good intuitively at calculating with. Okay, so we're about to take a break, so hang in there for just a moment. I want to talk about independence for a few slides. We know this multiplicative law, but let's suppose now that we have a particular case where the conditional probability of A given B. Now, A and B are just events, right? If I told you that A, let me back up. If I told you that B had occurred, and then I asked you what's now the probability of A, you'll recall that earlier we had an example where that changed, right? The answer probability of A changed based on the event that I asked you to condition on. But what if it doesn't change? What if knowledge that B has occurred does not change the probability of A? In other words, as you see in this equation, the conditional probability of A given B is the same as the unconditional probability of A. Well, what you would say intuitively is that B doesn't influence A. You might even use the word independence, right? Because that's what independence means as an English word. A and B are independent. Knowledge about B does not tell me anything about A. That's what independence actually is mathematically as well. So this equation depicts independent events. Full stop. It's just that simple. And I really prefer this definition because it's intuitively obvious. On the other hand, I have to admit that if you take it one step further and you multiply this out, right? So P of A given B, you can express that as the usual thing. It's the probability of the intersection divided by the P of B, and then you multiply both sides by P of B. You get this. So this second equation is the definition of independent events that you usually see presented. But to me, this is far less intuitive. I really prefer this one because it tells you what independence means. It means that B gives you no information about A. Now you combine that with the multiplicative law and you get the usual definition. Now, I will admit that in some sense, the second definition is slightly better because the second definition is also true and valid even if P of B equals 0. Whereas this conditional probability is undefined if P of B is equal to 0. So fair enough. This is a slightly more general definition of independent events, but this is the one that actually means something. It's not true for 3 events, by the way. It is not the case that independent events follow from this single equation here. And it's, again, if you want a homework assignment, try to come up with events that are obviously not independent, mutually independent by any reasonable standard of mutual independence, for which, nonetheless, this is still true. And I'll tell you, it's not really that hard to come up with such an example. If you wanted to try to define mutual independence for 3 events, you would need not only this equation, but also all of the two-way independent equations, right? So P of A and B is equal to the product of P of A times P of B, and for the other 2 as well. It's just sort of a side tangent about defining independent events when there are more than 2 of them. It's not something that comes up a lot. And by the way, it's not tricky if you're talking about random variables. So suddenly independence is exactly what it seems like it should be. If we're talking about random variables X, Y, and Z, then the definition of independence is exactly this, that if I were to give you 3 sets, S1, S2, and S3, and ask you what is the joint probability that X is in S1, Y is in S2, and Z is in S3, if that probability can always be expressed as the product of the 3 probabilities, no matter which 3 S1, S2, S3 I choose, then that is by definition 3 independent random variables. And this generalizes to more than 3, it generalizes to 2 as well. It's obviously 2 is a special case of this. Right, so for random variables at least, basically independence means that we can multiply probabilities, and that's super helpful. We use that fact all the time in a statistical context. And it is why so many of the theoretical results in statistics and probability start off with, let's assume that these random variables x1 through xn are independent of one another, right? Because it makes the math so much easier because you get to multiply individual probabilities then, instead of worrying about these crazy joint probabilities of multiple random variables. You can treat them individually and multiply them. Okay, so step away, refresh yourself, grab a bite to eat. It is after all noon on the East Coast of the United States. I have 1 more hour to go, but this is a terrific time to take a quick break. And maybe I'll just stare at the, and by the way, I apologize if you posted a question that I didn't get to. I tried to notice when something popped up. I'm sure that I wasn't always successful in doing that. Tatsuya asks a terrific question. Does P of A given B equals P of A imply the other way around? Yes, because independence is a symmetric event, okay? However, I'm so glad you asked that question, Tatsuya, because you cannot ever mistake P of A given B for P of B given A. That is a really common fallacy. In fact, it leads to, I could talk for quite a while about that. It's even a fallacy, and you may say, well, who would ever do that? I can cite an example where a woman was sent to prison for murdering her infants, partially based on a mistaken notion that P of A given B and P of B given A were the same thing, right? So this very common misconception can have literally tragic outcomes. Because of human beings' inability to understand sometimes the difference between those 2 things. So it's a terrific question lurking in your comment there, Tatsuya. The answer to your question is yes. Well, again, let me be perfectly technically correct. As long as both P of A and P of B are non-zero, then the answer is yes. Let's see. In other words, how do you verify that your partition is completely representative of omega? Kristen asks about representativeness. There is no claim of representativeness. And in fact, Kristen, if I can read a little bit into your question, this notion that you partition and in so doing end up with like equally likely slices, that can get you into a little bit of hot water. Oftentimes there's the notion that if I've sliced up my sample space and I don't know very much about the problem, then I should simply assume that everything is equally likely a priori. But then you could come along and be a little bit of a smart aleck and say, yeah, but maybe I'm going to readjust the sizes of your slices, right? So now what you started off with as a uniform prior distribution is no longer uniform. And all I did was change the pattern of slices, which doesn't seem like it's really changing the problem much in an important scientific way. So I guess, Kristen, again, to try to answer your question, how do we verify that the partition is completely representative of omega? I make no claims that it is. That is by itself kind of a fraught philosophical discussion at times, right? Sometimes there's an obvious partition, and sometimes we might even know a priori what the probability distribution is on that partition. But in general, we might not. Kristen asks again, is it possible to run into a problem with not knowing all B, the possible scenarios under which A may occur? Not knowing all B, yeah, short answer, yes. Short answer, yes. And I think here I'm not the authority to talk about good examples of that, but, and I hate to be piling up on Tom here, but I'll bet you Tom can address that question, Kristen. So hold that thought and ask somebody like Tom or one of our other speakers. Could you refer to some references on the philosophy behind the choice of frequentist and base? Wow, Maria Luisa, that's a terrific question. I'll tell you what, if you're really curious about this, you can go back to some of the like the founding folks of the statistical, I guess, explosion in the early 20th century. You can look for works of R.A. Fisher and J.B. Haldane in the late 20s, the 1920s and the early 1930s. They had back, almost 100 years ago now, this back and forth where Fisher was very vehemently on the side of, no, you can't bring your prior notions into this analysis at all. Whereas Haldane was arguing the opposite side, like, look, if you do that, you actually get some things for free. So Fisher versus Haldane is one of the debates I would cite there. And if you want another expert on that one, Maria Luisa, Joghesh Babu can tell you a little bit about that history as well. And he's one of our co-organizers. Repeat and or expand a bit on the philosophical question, Andrea or Andrea. So essentially, in a nutshell, we can't do Bayesian calculations unless we know the P of B. We can't do Bayesian calculations unless we have a prior probability distribution. But a prior probability distribution means that we have some a priori notion of what the truth is before we've ever observed our data. Remember, we want to know what is the probability distribution of B given A. We can't answer that question unless we know the a priori probability distribution of B. But philosophically, how can you justify bringing your a priori notions to a scientific question before you even observe the data? In a nutshell, that's the philosophical debate. And again, there's plenty of ways to justify it. So it's not a debate that many statisticians are overly concerned with. However, I will tell you this, we have at least one presenter today or whenever he's going. And I'm speaking of David Banks from Duke University. So Duke is an example of an entire department that has in its mission statement that this will be a Bayesian department. And David can correct me if I'm wrong about that, but it used to be the case that there is at least one example of a top-notch statistics department somewhere in the world, i.e. at Duke and maybe others, where basically the philosophical choice to go Bayesian has been made at a sort of a high administrative level. And that's kind of an interesting phenomenon in my book. But let's see. Is this the difference between Bayesians and frequentists? Absolutely right, Andres. You are exactly right. Those are the two terms. In other words, the non-Bayesian camp is often referred to as the frequentist camp. And there are probably gradations in there, and I don't claim to be an expert here, but by and large, that is exactly right. Michael Moss, is it correct to say that B is events and that A is the outcomes? The only thing I would change about that, Michael, is that I wouldn't call B the events. What I would say is that B are the parameters. So B is sort of like the underlying reality that changes the way that the data will be observed. And those parameters are things that you want to discover. So you're pretty close. And Michael's got a follow-up. Can we quickly return to the initial example with the die being rolled, but wanting to roll 1, 2, 3? Could we? Yeah, absolutely. We could label the different sets A and B and place them into Bayes. And by the way, in that example, we do know the a priori probabilities because I told you that it's a fair die to begin with. Right, so that's my a priori probability distribution. 1 has a probability 1/6, 2 has a probability 1/6, and so on. Right, I feel pretty comfortable bringing that prior distribution into this problem, and that is the prior in that situation. Okay. Giovanni Granata asks, was I referring to Sally Clark's story? That is exactly the story I was referring to when I said that the confusion between P of A given B and probability of B given A has, at least in part, led to a woman being convicted of murdering her children and being sent to prison. It's a super tragic story. Some people call it the worst miscarriage of justice in the history of Britain, blah, blah, blah. So there were egregious errors in the statistical analysis made by the prosecution that were not somehow corrected by the defense or in the justice proceedings. If possible, there are common places where astronomy papers make a mistake in statistics. Those specifically pointed out. Thanks. Wow, Maria, very good question. And I'll tell you this. I have, without being able to cite very specific examples off the top of my head, I have seen mistakes made in astronomy papers and statistics. That is becoming a rarity. And it's becoming a rarity partly because of the efforts of people like Jogesh and Eric and you all. There is now, it seems to me, a value in the astronomy community placed on knowledge of statistics as a tool to do astronomy. That has not been the case in the entire history of astronomy. I can't remember if Eric's talk has already occurred or not. Even though the birth of statistics was in astronomical problems, in the early 20th century, the two fields diverged. Statistics went more in a biological and sociological direction, and the physical sciences basically stayed away from statistics. And that has created some just egregiously bad statistical work in the physical science, in my opinion. However, you all, 358 of you, are here to tell us that that's actually changing. Right. So I hope I didn't paint a negative picture there, because I think I'm actually really optimistic. And again, I can't say enough about the efforts of Jogesh and Eric in somehow transforming, I think, an entire culture of astrostatistics, which I think scientifically is super valuable. All right, so I'm gonna move on, and I apologize for those of you who are continuing to ask questions that I'm not going to get to, but I know that folks are trying to answer these questions in the background as well. So let me just get back into the slides and talk about some specific examples of random variables. Okay, so here we go. A discrete random variable. First of all, we need to talk about something called expectation, which is just mean. So you see the word expectation in this context, you can think mean. That's totally fine. If x is a random variable, and as I said before, we can sometimes think of x as taking values, lowercase x1, lowercase x2, blah, blah, blah. In this case, let's assume that x has only finitely many possible values. little x1 through little xn. Then we can define the mean or the expectation, E of x, as well as the formula here. And this is no great shock to anybody who's ever done a calculation like this. You take each possible value x and you multiply by its corresponding probability, and then you add. And if you've seen the angle brackets in the literature, that's the same thing. Angle bracket x is the same as E of x. And I'll tell you right off the bat, I know I do not like that notation. I do not like writing angle brackets x. I much prefer E of x. And one of the reasons, well, maybe the only reason, is that I have actually seen, I referred to some egregious errors that I've seen. One of them that springs to mind was conflating angle brackets x with x itself. Talk about the properties of the random variable as though they are the same as the properties of the expectation. That is totally false, right? This x is a complicated function, right? It's a function from the sample space to the reals. It has this randomness built in. E of x is just a real number. That's all it is. It's a number, right? It's a constant. And so capital X and its expectation are completely different animals. And if you just write angle brackets x, I think it's a little bit too easy to mistake those two ideas. So that's why I don't like that notation, but it's more common in the physical sciences, I understand that. And I'm not saying that you shouldn't write that way. I just want you to be aware that this is not the same as the random variable x. It's really easy to calculate the expectation of a function of x. Let's suppose that we define a new random variable y, which is by definition g of x, where g is some known function. Then you can do this plug-in calculation. And this is pretty obvious. It's not so obvious when we go to the non-discrete case, but I'll just sort of throw that out there. We simply take the possible values of x, hit them with the g function, and then again, multiply by the corresponding probabilities. And of course, this does not differ from the same definition up here, right? If you were just to add y's here, well, the yi would be the same thing as the g of the xi. And the probability that capital Y is equal to is equal to yi would be the same thing as the capital X being xi, right? Because we're defining y as a function of x, right? So this is not actually all that earth-shaking. One of the functions of x whose expectation we care about is the difference between x and its mean squared. And when I take the expectation of said random variable, in other words, the expectation of x minus mu quantity squared, where mu itself is E of x, then that's the variance by definition. That's what I call the variance. Okay, so turns out that expectation is a linear operator. And so in other words, for any a and b, as long as it makes sense to talk about ax plus by, right? If those two random variables actually have a well-defined sum, then the expectation of the sum is the sum of the expectations. Furthermore, we can pull constant multiples out in front of the expectation operator, okay? So expectation is nicely linear. Variance is not. Variance is not a linear operator, but we'll get to that in a sec. The other thing I'll tell you is that this definition of variance at the bottom, the expectation of the square of x minus mu, is not usually the easiest formula with which to calculate. So almost every time I want to actually calculate a variance, I think of the variance as the expectation of the square minus the square of the expectation. And you can verify that fact based on the linearity of the expectation operator. If you want a quick homework problem, that's pretty easy. Okay. Again, usually that second expression is the easier one to use computationally. Okay. And variance has something to do with spread. I've depicted here two random variables. One of them takes values plus and minus 1. One of them takes values plus and minus 10. Let's suppose that those values are taken equally likely. Obviously, the red one, the plus minus 1, has a smaller variance than the green one that takes plus and minus 10. Furthermore, the variances in this case are easy to calculate. If we assume, again, that plus minus 1 has equal likelihood, then that means the expectation is 0. Remember that the variance is the expectation of the square minus the square of the expectation. So the expectation being 0, in this case, the variance of each random variable is simply the expectation of the square. And the square of each of these variables turns out to be a constant, right? So the red variable has variance 1 and the green variable has variance 100. Okay. And I should also mention, like, standard deviation is the square root of variance. That's just a definition, right? So standard deviation, and the reason that we use standard deviation is because that now takes us back to the original scale of the variable, right? Because variance squares that scale. And so variance is not that helpful if we're trying to judge the magnitude of the variance. Whereas when we take the square root, now we're back on the original scale. So that's why standard deviation is often used. Not all random variables have an expectation. This is just, again, sort of one of these mathematical oddities, but you just have to be careful when you write E of X. Not all X actually have a well-defined E of X. And it's not just that you could say, well, then it'd be infinity. No, there are some random variables like the one seen here where there is simply no sensible way of defining E of X. Even though, you know, it's symmetric about 0, right? You still can't call 0 in any meaningful way the mean or the expectation. So we're not going to talk too much about this. I just wanted to sort of alert you to the fact that expectations and variances need not exist. And in fact, this does occasionally come up. Physicists and astronomers often use something called a Pareto distribution. A Pareto distribution doesn't always have moments. It doesn't always have an expectation or a variance, depending upon how it's defined. So at any rate, it's something that sometimes actually comes up. Okay. I advertise this section as being about specific cases of random variables. I'll start with the binomial random variable. Binomial random variable very quickly. And I'm going to, by the way, just so you know, I'm going to go through these next slides somewhat quickly. I'm not going to step through every bullet point. But again, you have access to those slides on the website of the summer school. So a binomial random variable is a random variable that counts the number of successes if you take a series of independent and identical trials with probability, let's say, P of success on each trial, and then 1 minus P of failure on each trial. And so basically it's like the coin flip distribution, right? If you count the number of heads in a bunch of coin flips where the coin might not be 50-50, but rather P and 1 minus P, then the count of heads is a binomial random variable. What I've done for you here is to show you its mean and its variance. I'm not going to talk too much about this, except I do want to just point out a couple of things to try to help cement some of these concepts for you. So I've said here that the variance of X is n times P times 1 minus P. Let's consider the special case where n is 1. So we're only doing a single coin flip. So X, the count of heads, can be either 0 or 1. Those are the only two possible values that it can take. Okay, well, if it takes 1 with probability P, okay, well, then that means we can find its mean. It's just P, right? Because to find the mean, we multiply all the possible values by their corresponding probabilities, and we get P. Now, what about the variance? Well, the variance is the expectation of the square minus the square of the expectation. But in the case of a 0-1 random variable, the square is the same as the random variable. So when I say take the expectation of the square of X, that's the same as taking the expectation of X itself. That's P. So the variance is P minus the square of the expectation. P minus P squared. That's where we get P times 1 minus P. Okay, so in the special case where n equals 1, the mean and the variance are pretty easy to calculate, and I'm just going to leave it at that. I also wanted to point out that the binomial comes up a lot in various guises, including in the astronomical literature. Here's another very important random variable that happens to be discrete. It's called a Poisson random variable. It's often used to model counts of things. For instance, if you've got a Geiger counter and you measure how many clicks you get in a fixed amount of time, that is going to be a count. That number will be a count, and it is modeled very well by a Poisson distribution because the physical processes underlying it actually give rise to a Poisson distribution. Okay, so Poisson is a useful distribution in many ways. Its probability mass function is kind of interesting here. I'm not going to delve into this, but I do want to point out that the lowercase y here has no upper bound. Because this is a model for counts, the possible values that the random variable can take begin with 0, then 1, 2, 3, but there is no upper bound. And the probability for any particular y can be ground out by just plugging in the y in the 2 spots that you see. The lambda is a fixed number. It turns out that it's the same as the expectation. It also turns out that lambda is the same as the variance. So a Poisson random variable has the distinguishing feature that its mean and its variance must be the same. That is not always a very good way of modeling counts, because when you assume a Poisson model for counts, you are assuming automatically that your standard deviation is the square root of your mean. And if your particular counts don't have that property, then Poisson is probably not your friend, okay? On the other hand, and Poissons occur in the literature, again, all the time. On the other hand, there is a way that you can model counts that sort of frees you from that stricture, that the mean and the variance are of the same number. And we'll build up to that. So first, let's consider a geometric random variable. A geometric random variable is the number of coin flips you have to sit through in order to get to your first head. Okay, so if x is that number, well, then what could x be? Could be 0. Like maybe I didn't have to wait at all. Maybe my very first coin flip was a head. Could be 1. Maybe I had one tail followed by a head, so I had to wait for one tail first. Could be 2, could be 3. How many tails did I have to wait through? There is no upper limit to that number, right? So this is another example of a case of a discrete random variable where the number of possible values is countably infinite, okay? It's the number of tails you have to sit through before you get your first head. And here's what the PMF looks like. Now, if you start with that geometric idea, but now you say, well, how many times do I have to wait in order to get to n heads? Well, you're just going to add a bunch of geometrics together, right? So if I want to say, well, how long do I have to wait before I get my third head? Well, what I'm going to do is I'm going to take a geometric for the first head and add it to a geometric for the second, and then a geometric for the third. Those will all be independent. So I have the sum of independent geometrics, and I build up something called a negative binomial. Now, the negative binomial has a nice story associated with it. I just told you it's a sum of geometrics, which means it's the waiting time until you see the, in this case, rth success. On the other hand, that's not often the way the negative binomial is used in practice. The negative binomial is the thing that I was referring to earlier. If the Poisson is not your friend, because the Poisson has this constraint that the mean and the variance are identical, negative binomial actually has 2 different parameters. And so a negative binomial is a model for count data that allows the mean and the variance to be different from one another. And so a lot of times you see a negative binomial in the literature, and it's not because there's a belief that the underlying physical process is actually something like the sum of geometrics. It's not like we're waiting for the rth repetition of some geometrically distributed event. No, it's simply because this is a more flexible distribution than the Poisson. Okay, so that's kind of a super fast look at some discrete distributions. Let's now talk about continuous distributions. Continuous, I have to be careful. Everybody wants to say continuous random variables. Well, okay. Remember though, the random variable by definition is a function. So whenever I say continuous random variable, what I'm really saying is continuous function, but that's not what it is. A continuous distribution is referring to the distribution function of a random variable, which is not the random variable itself, okay? And so it's just a bit of a slight notational, I guess, terminological problem. It's still, people do it all the time. They talk all the time about discrete random variables and continuous random variables, even though technically speaking, continuous random variable is not the right way of describing a continuous distribution. So anyway, I digress a little bit. Basically what we're doing is we're replacing the sums from the discrete world by integrals. Right? So now we have this capital F function. Capital F is defined as the distribution function. Sometimes it's called the cumulative distribution function, or CDF. And the reason that it's called cumulative is because by definition, capital F evaluated at X is the cumulative probability up till X. In other words, F of X, big F of X, is equal to the probability that X takes any value less than or equal to little x. That's why it's called the cumulative distribution function. And if you think through it, you'll notice that this means that capital F must be non-decreasing. In other words, if you take lowercase x and make it slightly larger, you can't possibly have diminished the probability on the right-hand side, right? So it's a non-decreasing function in x. It can't go any higher than 1 because it's a probability, and it can't go any lower than 0 because it's a probability. And in fact, the limit out on the left-hand side at -infinity is always 0, and the limit out on the right-hand side at +infinity is always 1, right? So there's one additional feature here, that it has to be continuous from the left, but well, let me just not get into the technical stuff. The one thing that is of interest in the case of a continuous distribution is that the density function, which is here depicted by lowercase f, can be expressed as the derivative of the CDF, okay? And you can see that, I mean, it's sort of a fundamental theorem of calculus result. When you look at f as an integral from -infinity up to x of this density function, right? Well, we say that there exists a function f, which we will call the density, such that this is true. And if that's the case, then clearly that lowercase f could possibly be the derivative, assuming that capital F is differentiable. I should also add that capital F always exists for any random variable. This integral might not always make sense. There might not always be a lowercase f. And in fact, it's precisely in the cases of the continuous distributions that we do have this lowercase f. Density is a term that we use for lowercase f. Sometimes density is also used for PMFs, depending on the context. In an introductory probability setting, we try to keep the mass function and the density completely separate. But later on, you sort of unify these ideas and you just talk about a density function. And in fact, Bayes' rule is an expression involving densities, right? The posterior density of the parameters we care about can be expressed as the product of the likelihood and the prior density up to a constant. Okay. Yeah, so I just wanted to make the point that typically we use a capital letter for the CDF and a lowercase letter for the density, which is oftentimes taken to be the derivative of the capital function. I already mentioned that capital F has these properties. And in fact, the converse is also true. The converse, in other words, anytime you have a function that has a limit of 0 at -infinity, a limit of 1 at +infinity, that is non-decreasing and continuous from the left, that is a CDF for some random variable, right? Okay, let's see, what else do I want to say? Yeah, I already talked about this note at the bottom here. So let me just move on to some examples. This is one of the most common distributions. Of course, you all know what the most common distribution is. All of you are familiar with the Gaussian, the normal, I'm sure, the bell curve, right? So that's probably the big continuous distribution. But an exponential, this is the analog of the geometric distribution, right? So the geometric distribution was how long do we have to wait until we see the first head? Well, let's suppose that instead of that, we are measuring time in continuous terms. And the question is, how long do we have to wait before we see the first click from our Geiger counter? The answer to that question is an exponential random variable, an exponential waiting time, right? And in fact, the relationship between exponential waiting time and Poisson counts is one of the cool aspects of this probability theory. But I'm getting a little bit ahead of myself. So there's an exponential distribution. Here is its density. It has a closed form for its CDF, or capital F. We can simply find it using a straight first-year calculus. And so the exponential distribution is very well behaved, very well understood. Of course, it's only valid on the positive real line. So you can't have a negative value that is an exponential random variable. Here's your normal. And if you've ever seen any treatment of the normal distribution, like in a probability class, you've probably come across this formula for its density function. Pretty much useless, by the way. The density function is good for almost nothing as far as I'm aware. So memorizing the density function of a normal is not super helpful. I don't know. There are some times when you get into trouble for quoting me on that, but generally speaking, it's just not a helpful density function. On the other hand, knowing some features of the normal distribution is helpful. Here's the characteristic shape. You can identify these things according to their spread and their center, right? Those are the two values that you need to define a normal density function or a normal distribution: mean, mu, and variance, sigma squared. Or standard deviation sigma is another way of saying that. The CDF is not nicely behaved. There is no closed form for a normal CDF. And that's kind of a sad thing because it's such a common distribution. It would be great if there were some, analytical expression for the CDF of a normal distribution. Unfortunately, it does not exist. And so you have to evaluate a normal distribution's CDF numerically. And this happens, by the way, all the time. If you've ever done a 95% confidence interval and used plus and minus 1.96, that 1.96 came from a numerical evaluation of the CDF of a normal distribution. And if you have no idea what I just said, it's okay, hold that thought, it'll come back later this week. The log normal distribution is sort of unfortunately named because log normal sounds like log of normal. It's not. It's the opposite. So in other words, the log normal is an exponentiation of a normal distribution, or stated differently, the log of a log normal is normal. Okay, so, and that's basically all you need to know about that. I will also tell you that if you stare at this long enough, you can see the density function of a normal distribution lurking therein. And in fact, that's true. You can see that how do I want to say this? If I were to tell you that my log normal was e raised to the power of a normal, e raised to the power of a normal, then you could, based on that fact, derive the density function for a log normal distribution. And it would have the normal density function hiding there. And it would also have the Jacobian of that transformation hiding there. Okay. So it's like, there's a change of variables. Change of variables back from your multivariate calculus class shows up in probability theory as well. Okay. Yeah, expectation, it does not change. Instead of summing, right, instead of taking the sum of all possible values x multiplied by the corresponding probabilities, you take the integral of all possible values x multiplied by the density function, right? So the formula is the same, except that it's going to involve an integral rather than a sum. The variance is still the same. It is still the expectation of the square of x minus its mean. It is still given by the expectation of the square minus the square of the expectation, right? So that doesn't change whether you're doing sums or integrals. I actually kind of forgot what I was doing here. So there's the log normal and the normal. And I think I'm actually, just in the interest of time and too much Zoom sitting in front of a screen, I'm going to skip this and head to our last break before we launch into the final section. So again, feel free to get up, wander around, come back in 3 to 5 minutes, get a drink of water. Let's see. Okay. So P of B is accurate so far as we assume we understand all the factors that led to the outcome B. Boy, Sam Fetterman, forgive me, I've lost the context of your question, so I'm not entirely sure in what context that question is coming. In fact, it may be that, Sam, you're actually having a dialogue with one of the instructors, in which case I should probably just close my mouth and let them continue that with you.
I think that's on prior distributions about parameters.
Okay. All the factors that lead to outcome B. Yeah, so in Sam, in that when we're talking about P of B in this context, we're talking about the probability distribution of parameters. Now, we've just seen a bunch of particular distributions, right? We saw things like binomial, we saw things like Poisson, we saw things like normal. Each of those have these values that determine the distributions. In the case of the normal, it was the mean and the variance, right? It's mu and sigma squared. Those are the parameters, and those are things that we would like to learn about, right? Because again, if we know things are normal, then all we need to know is mu and sigma squared. So that's what we're going to try to learn from our data. If you're doing a Bayesian calculation, you have to give me some prior notion of how mu and sigma squared are distributed. And that's before you even look at your data, right? So your data will give you more information, obviously, about mu and sigma squared, but you have to tell me a priori. And so do we assume that we know all the factors that led to the mu and the sigma squared? Well, not necessarily. Scientifically, if we knew all of this, then we wouldn't be needing to ask the question. However, we may believe that we know something. We may have some information about what mu and sigma squared should be in this problem. And now we're going to go out and do an experiment that will give us more information about mu and sigma squared, right? So we're going to combine P of mu sigma, in this case, P of B, or in your question, with the data that we observe. And we're going to grind out what's called the posterior distribution of mu and sigma squared. And that'll teach us it will mathematically combine for us what we knew prior and what we observed in the data set. Great question by Pi, and I hope I'm pronouncing your first name correctly, Pi. So the point that Pi is making is that there are a lot of mistakes that assumptions are made that are not met. That is correct. On the other hand, I'll tell you that is not unique to astrostatistics. So that's true across the board, right? So if you want to talk about statistical mistakes, by statisticians as well, we're not off the hook for this. Quite often assumptions are made that are not realistic. And sometimes there's a good reason for this, or at least a defensible reason. And it's simply because, in mathematics, a model is never the same as reality. We have to make some simplifying assumptions or simply can't make any progress, right? And so sometimes you make assumptions that are not quite correct, but you hope are not egregiously false, right? So yeah, you're absolutely right, Pi, but I would say that's not on the astrostats community necessarily, because everybody does that. And I saw that Jogesh was answering that question as well. So he maybe has
this may be a question for Slack channel. There may be good discussion there.
Fabulous. That's a great
and
idea.
Also, I want to quote Box saying that all models are incorrect.
Yes. Well, and then there's the second one, right? The second part of that. All models are wrong, but some are useful. Which I think is an important second part of that quotation. And it's, they attribute it to Box. Jogesh, has that been actually verified? Is that actually George Box, or is that just one of those things where Box may have said it, or? No,
Box never said it, but many people.
That's what I thought, yeah, okay.
Say that.
They all say that he said it, right? Yeah. Yeah. All right, well, let's march on toward the 1 o'clock hour, because this is a lot. It's a lot to slog through on Zoom. I know we've all been doing it for the last, gosh, how many months? 14 months, 15 months. And I know it's not necessarily easy. So we're doing the best we can, right? So here we go. Okay, some limit theorems to wind up. And if we don't get through all of this, it's totally fine. So let's suppose that we conduct an experiment many times. And let's suppose, like in the sort of the standard statistical paradigm, X represents some random variable whose outcome is determined by an experiment. Let's also suppose now that we're going to run that experiment n times, right? Where n is, well, you know, you may have seen n referred to as the sample size, and that's true in this case as well. But here it just means the number of repetitions of our probability experiment. So it's quite frequently the case that you see a statement like you see at the bottom of this slide, where x1 through xn will be IID, which stands for independent and identically distributed random variables. So this IID framework is super common in statistics. As I mentioned previously in this lecture, the independence is often used because mathematically it just makes things much more tractable, right? Because it means that now these x's, which have some complicated joint distribution, well, maybe not so complicated, right? Because the joint distribution of the x's can now be expressed as the product of their individual distributions. That's what independence buys you. And so that's the first I. The ID part comes from the context of the experiment, right? It's often the case that we as experimenters tried to do the same thing many times. It sort of goes back to the very first slide I showed you, this prologue, where this patient was shown a set of pictures 17 times. The idea is to do this 17 repetitions. We want each repetition to be the same as the others. Okay, so that's the ID part, the identically distributed part. So we have x1 through xn that represent our data taken as a group. Okay, so there we go. So I'm going to give you an example of such a set of experiments. And it's in some sense like the simplest possible experiment, right? And people always roll their eyes when coin flips come up in a probability class, right? Because like, nobody's flipping coins, nobody's rolling dice. We're trying to do science, right? Well, just bear with me because there's some surprising, I think, and beautiful structure that emerges even from the simplest of probability experiments. And the one thing that you can say about the coin flip is that it's a simple experiment, right? So in this case, I'm going to flip a coin, and if I get heads, I win $1. If I get tails, I lose $1, right? So I'm playing against an opponent somehow, right? So my outcomes, where x will be my outcome for a particular game, x sub I on the ith game. It's either +1 or -1. And I'm going to assume that my coin is fair. So I have a probability of 1/2 of +1, a probability of 1/2 of -1. Those are the only two values that x sub I can take. I'm going to assume that I repeat this experiment, this game, n times. So n is my sample size. Okay. At the end of the day, then, if I want to know how much I won, the answer is S. So you'll notice here that I've defined S sub n. S sub n is the sum of the x's. S sub n therefore represents my total winnings in n repetitions of this game. I'm going to assume that the coin flips are independent of one another. Of course, that's the physical reality of coin flips, right? So I have now summed independent and identically distributed random variables. And I'm going to express that sum as S. And there's just some fantastic stuff that happens to S in the limit as n goes to infinity. So let's just look at a few simple calculations. I can think of 10 games, right? Like what happens if I play this game twice? And I can ask myself, well, what's the probability that I lose at least 6 times out of 10? Right? So you do the math, that means that my winnings end up being less than -2. What's the probability that S sub 10 is less than or equal to -2, right? Well, that could happen, right? The probability that happens is 38%. But let's now take that let's multiply everything by 10, okay? So let's suppose I play this game 100 times now. And once again, I want to think about losing 60% of the time. What's the probability that I lose at least 60 out of 100, which is to say that S sub 100 is less than or equal to 20 now. This is suddenly less likely. And if I multiply once again by 10 and ask what's the probability that I lose at least 60% of the time in 1,000 games, we're now in the realm of essentially impossible. That's never going to happen, right? And so there's something there that's happening, right? That Obviously I wouldn't expect to lose 60% of the time, but if I only play 10 games, well, it could happen, right? It still could happen. Whereas if I play 1,000 times, it's not going to happen. So just to lend some formality to this, we will introduce something called X bar. X bar is the sample mean. So it's a mean, but it's also a random variable. And this is where things get super confusing for introductory statistics students, because earlier I used the word mean for mu. Mu is not random. Mu is a fixed constant. It's equal to the expectation of X. It's what I get when I integrate, I take X times its density and integrate over the whole real line. Okay, so mu is a constant, but it's also a mean. X bar is a random variable because it consists of the sum of the xi's divided by n. It's the way that you've learned to calculate the mean since, probably you were an elementary school student. Okay, so now because X bar is a random variable, I can talk about its mean. And this is, did I mention this gets confusing, right? So I can talk about the mean of the sample mean. What do you think the mean of the sample mean is? It's the mean. So the mean of the mean is the mean, actually has meaning. And I'm sorry for that pun, but we really do have a sense in which the sample mean as a random variable has a mean that is equal to the same mean as the initial x's, okay? And again, that gets super confusing. We're going to talk about the distributional properties of this sample mean X bar. Here we go. Here's one of them. If I take any epsilon, any positive epsilon, and I look at the event that X bar minus mu, now remember, X bar has a mean equal to mu, okay? So what I'm looking at now is the event that X bar differs from its own mean as a random variable by an amount that's greater than epsilon. For any epsilon that I want to choose, no matter how small, the probability of this event will tend to 0 as n tends to infinity. In other words, it's extremely likely that I will find X bar within epsilon of mu for any epsilon as n gets large. And that's called the law of large numbers. It says that essentially over time, X bar will look like mu. It will get very close to mu. It's sometimes misunderstood. And I'm just depicting graphically what happens over time, right? The true mean in this particular experiment is 0, and you can see that the sample mean over time sort of, bounces around, especially at first. There's a lot more variation at first, but after a while, it converges to its true mean of 0. When I say in this slide that it's often misunderstood, there's something called sometimes the law of small numbers. It's referred to sometimes as the law of small numbers. It's also known as the gambler's fallacy. It's the notion that because the law of large numbers is a thing, and everybody knows somehow that there is a law of large numbers, right? That somehow that means that if I've played a game for 10 repetitions and I've lost 10 in a row, that somehow I'm more likely to win the next time. Now, I think all of you could recognize that as untrue, right? The 11th game has no memory of what happened. But then how do we jibe, how do we square that with the fact that there is a law of large numbers? This is legit, right? How is it that the 11th game doesn't correct for the 10 games that I lost? Well, the answer is as follows. The law of large numbers operates by overwhelming, not by compensating. Okay, so when you see somebody trying to argue that, well, something has happened a lot in the past, and therefore it's going to correct because of the law of large numbers, you say, no, that's a fallacy. That's the law of small numbers. And that string of bad luck that you've just experienced will be completely overwhelmed if you run this forward another gazillion times, right? So once again, the law of large numbers operates by overwhelming, not by compensating. So this takes me right at the end of the talk to essentially my favorite topic in probability, and it's because it's just so beautiful. I would say that the central limit theorem is as close as we have to a fundamental theorem of probability. There isn't such like, I've never heard anybody refer to this as the fundamental theorem of probability, but we do have the fundamental theorem of arithmetic, the fundamental theorem of calculus. And so if there were a fundamental theorem of probability, I would certainly vote for the central limit theorem as it. So how does it operate? Well, let me just show you the first line in this table. So let's go back to thinking about S1000. Okay, now, turns out that the variance of S1000 is equal to 1000, right? Because S1000 is the sum of 1000 x's. Each x has a mean of 0. Each x has a variance of 1, because remember, it can be plus or minus 1. The variance of x is the expectation of the square minus the square of the expectation. Each of those x squares is always the constant 1. And the expectation of each of those x's is 0. So the variance of each x is 1 minus 0 squared. Okay? Turns out that because the x's are independent, the variance will sum. So the variance of Sn is the sum of the variances. And by the way, that is one of the really cool facts about variance that I haven't mentioned yet. I think I may have put it on on my last break slide. I forgot to highlight it. But when you have independent random variables, the variance of their sum is the sum of their variances. That's not true generally. So the variance of S1000 is 1000. Which means that the standard deviation of S1000 is the square root of 1000. And so when you look at the random variable defined as S1000 divided by the square root of 1000, what you're looking at is a variable that has been shifted to its center by subtracting 0, because remember, S1000 has an expectation of 0. So we're going to subtract a 0 to shift it so that it's centered at 0. Then we're going to divide by its standard deviation. And the resulting random variable, S1000 over root 1000, has a standard deviation of 1. So it has a mean 0 and a standard deviation of 1 and a variance of 1 as well. Okay, so this is a standardized random variable. We know its mean and its variance. The astonishing fact is that not only do we know its mean and its variance, but we know roughly its shape, and that shape is normal. That's crazy. If you think about where this came from, all we're doing is adding pluses and minuses, right? Plus 1 and minus 1. Why on earth would the shape of S1000 over 1000 look normal? Why would it look Gaussian? Why would it look bell-shaped? This to me is beautiful mathematics. Again, we know that its mean is 0 and its variance is 1. That we did just by standardizing this. That's no mystery at all. The mystery is the shape of this distribution. And we can see it start to take shape here. Basically, this is just a tabular summary of some of the properties of S1000 over root 1000. And here you have the exact probabilities. Here you have the probabilities of an exact normal distribution. And the point of this table is simply that the two columns look surprisingly close together, okay? So when n is 1,000, our S1000 behaves a lot like a standard normal distribution after you standardize it. Let's see. And this fact, the fact that the standardized sum of independent random variables behaves like a standard normal is called the central limit theorem. And it really didn't matter that I started with the sum of x's that were plus and minus 1. In fact, it didn't even matter that the x's were identically distributed. It's the independence of the x's that really leads to this normal shape. If I sum a lot of these things. Yeah, there are some ways that you can construct pathological examples. But if you're careful about how you define what these x's are and what their properties are, then it doesn't matter what their shape is. It doesn't matter that our x's had only two possible values, plus 1 and minus 1. I could have started with any x's I wanted to, as long as I sum up multiple copies of them that are independent. What I'm going to get is going to look very normal as n gets closer and closer, well, as n gets larger and larger. And that's the central limit theory. It's just absolutely beautiful mathematics. There's some summary of it right here on this slide. But to wrap up, I'm just going to show you a couple of things. So here is a histogram depiction of what happens to Sn as n gets larger and larger. So on the top here, you see 100 trials. So this is what happens when n is 100. And remember, I could win or lose. And I guess the number of successes here is what I'm plotting, not my winnings, right? Because my winnings would be centered at 0. So this is the number of successes. Out of 100, you can see that 50 is the modal value, but this astonishing bell shape is here almost magically, right? And it gets even more normal as n gets larger. Here is n equals 400, here is n equals 900. And if you wanted to, you could actually see quantitatively what's happening here. You'll notice that the shapes are the same, but the scales are changing. So when you go from 100 to 400, that's actually multiplying n by 4, which means that the standard deviation is going to be divided by the square root of 4. When you go from 100 to 900, you're multiplying by 9, which means that the standard deviation is divided by the square root of 9. And you can verify that from the picture here. And so let's see, with that, I'm just going to leave this slide here for a moment. There's all sorts of just astonishing structure in the asymptotics results here. And this law of the iterated logarithm is again, it's sort of one of these mind-blowing things that just sort of happens as you start studying the behavior of sums of independent random variables. I'm not going to talk you through the law of the iterated logarithm. If you want, you can Google it. You can stare at this slide and try to make sense of it. I really think that the central limit theorem is, like I said, the fundamental theorem of probability. And so if you take nothing else away from this discussion of limits other than the central limit theorem, then I hope you do take that away. And I see that it's now 1 o'clock. So why don't we call that it for this lecture?
Thank you, David, for your lecture. There are a couple of questions on the Q&A. I don't know whether.
What about the error function in terms of the CDF of a Gaussian? Yeah, so I think you mean by error function, I think you mean the thing defined as the error function, which is like, I can't remember, it's like 1 minus, oh dear, what is the error function defined? Like ERF, right? Is that what you meant, Nicolina? The ERF function? It's basically just a scale and translation version of the CDF of a normal, right? So yeah, and I see Claire is going to answer that. That's fantastic. Yeah, so the error function, which I think is what you're referring to, and the CDF of the standard normal, I don't want to call them the same, but they're sort of very easily definable functions of one another. What happens quite often in modeling and science? Okay, Eric Feigelson is answering Aaron's question. Yeah, wonderful. By the way, thank you all for the terrific questions, and thanks to everybody that's been answering them. I know Claire's name has come up. I know Eric Feigelson, Tom Laredo, Jogesh, Babu have answered some. I'm probably leaving out some names. I really
and
appreciate.
Ian also is answering some.
Ian, yes, thank you, Ian, for yeah, this is just wonderful. So I hope that was informative and that we got all of your questions answered.
If the participants have some more questions after the lecture is over, they can put them in Slack channel so that when David has time, he can answer those things later on.
Absolutely. And in fact, that you've just reminded me, Jogesh, I need to make sure that I got that link that you posted at the beginning to, that was Tak that posted the link.
Yeah, either Tak or Bob can resend you that.
Wonderful. Yeah. And I should also add, any of you participants, you're welcome to contact me via email, like long after this event, if you want to. That's totally fine. I'm easy to find on Penn State's website, obviously. So feel free to do that if you don't get your questions answered over the course of this week. Thank you very much.
Okay, guys, we'll meet again at 1:30 Eastern Daylight Time. That is, I don't know. You had to convert the times from your location. I don't know exactly what it is for different locations.